the title of this is it a car? Is it a computer? No, it's the Raspberry Pi Java Carputer. And this has been a session which I created last year as part of the work I was doing for Java 1. And it's certainly been a lot of fun. I've continued to work on this project over time. And I've had an awful lot of fun actually doing this. Because I have to admit, I am a geek. So I like things technical. I like things electronic and computers and things like that. Hence the job that I'm in. But I'm also a petrol-head. So I like watching Top Gear, and I like watching things about cars and stuff like that. So what I've done is I've combined these two passions into one thing, which is the Carputer. Now, as an Oracle employee, the first slide that I always have to put up is the legal slide. And basically this says that we're not committing anything in terms of our future product direction in what I'm telling you. I think I'm pretty safe that that is actually the case. So I think we can move on from that fairly quickly. In terms of the agenda for this presentation, what I'm going to do is I'm going to start off talking a bit about cars and computers in general, and a little bit about how things have changed over time, and what we're actually looking at today, because it's very interesting in terms of how computers are used in cars. Talk a little bit about Raspberry Pi and why I selected the Raspberry Pi as the device that I used to create my in-car system. And then we'll dig into how we can use Java, embedded Java, JavaFX, to actually build the system that I've got here. And then at the end, I'm going to give you some demos. Now, you may notice that I have no car actually in the room, so I'm a bit limited in terms of doing an in-car system demo. But what I do have is the system that I built. I've got it here. I'll be able to show you that in action. And basically, I'll replay some data that I recorded when I was actually using my car. Let's start. There are actually seats at the front if you want to sit in the front row. So let's start by talking about cars and computers, because this is, as I say, interesting to see how things have changed over time. And what I did was I actually went back and I did a bit of research. So here is my first car, the Mini Clubman. So who here has ever owned a Mini? Anybody? Oh, a couple of people, right. Mini is a lovely car, the original Mini. I'm not saying that the new Mini is bad, but the old Mini was a lovely car because it was so simple in terms of how it was constructed and the technologies that were used in there. And literally, there are no electronics at all in this car, unless you count the radio. And once that was stolen, as it was, then there were no electronics in my car at all. It is purely electromechanical. So it has these things called points and a distributor. Who remembers points and a distributor? A few people. Feeler gauge, yep, remember those things. Not many hands going up here, that's interesting. It had a thing called a carburetor and a manual choke. Again, who remembers the choke? Yep, okay, more people remember the choke, good. It had drum brakes, it had a dynamo. Didn't even have an alternator, it had a dynamo. And then for the luxury items, it had lights, it had a horn, it had wipers that sometimes worked. It had a fan that would work if you stuck your finger around the back and actually spun it when you switched it on, and then it would actually start. And then an ignition switch. Now, if you look at the wiring diagram, because what I did was I still have the Haynes manual. This is the sad person that I am. I still have the Haynes manual for my Mini. And so I took a copy of the wiring diagram for that. And as you can see, it's reasonably complicated. Even with that small number of electric devices on there, it's a reasonably complicated diagram. Lots of connections between lots of different things. So let's move forward to, well, 2011. And this is my current car. I have an Audi. And this one actually has lots of electronics on it. I purposely bought it because it had lots of interesting features and electronics on it. So for a start, it has an engine control unit. And that means that the engine, the amount of fuel, the amount of air, the way the engine works is actually controlled by a computer. And the nice thing about that is you can actually reprogram the computer and change the amount of power that you can get from the computer. So not on this particular car, but on a previous car I've had, I actually had it remapped and I was able to get more power out of the car just by changing the way that the computer worked. It has fuel injection, it has electronic timing, so there's none of this points and feeler gauges or anything like that. The throttle is fly-by-wire, so there's no physical connection between the throttle pedal and the actual engine. It's an electronic thing where you measure the resistance, and then you feed that information to the electronic management system, and it actually changes the speed of the engine. It has anti-lock brakes. It has a thing called the Electronic Stability Program, or ESP. I've got to say that a friend of mine has a BMW, and he pointed out that the manual says that ESP, and Electronic Stability Program, is all about making sure that you're safer when you drive. So if you go around a corner too quickly, it can adjust the braking on different wheels to try and correct understeer or oversteer. And in the BMW manual, it actually says, be aware that the Electronic Stability Program cannot defy the laws of physics, which is actually quite true, so you can't do that. It has a thing called magnetorheological suspension. So the suspension system actually has fluid in it, which has magnetic particles in it. And then you can apply an electric field to that, vary the electric field, and then vary the viscosity of the suspension system. So you can change whether it's comfortable or uncomfortable. That seems to be the two modes that it has. It has satellite navigation. It has all sorts of things like auto-sensing wipers and lights and things like that. So what does the wiring diagram look like for that? Well, it's actually a lot simpler because there's too many things to wire everything directly. You can't say, okay, well, here's a light, I'll wire that to a switch, or wire the switch to something else. So what we now have is a bus architecture, something we're all familiar with in terms of electronics and computers. And in terms of like the Audi system, there's 3 different buses in the car. You've got one for what's called the convenience bus, which is like the wipers and the lights, things like that. You've got the infotainment bus, which connects the satellite navigation, the speakers, and things like that. And then you've got the powertrain bus, which is the engine management system, the throttle, and all the sort of important things. And the idea of having multiple buses is that you don't want the information to get congested on one particular bus. And so we have different buses for different signals. In terms of actually making use of this, what you'll find is if you look underneath the dashboard of your car, you will find a socket. It looks a bit like an old SCART connector. And what that does is allows the garage to connect a device to it and then be able to read information about whether there are any faults that have been detected in your car. And one of the nice things is that you can go onto eBay and you can buy a box like this, which costs about, well, £10. And it will also plug into the same connector. And that allows you to access the information that the garage can access. And we'll talk more about that as we go through. This is called the OBD2 interface, Onboard Diagnostics Interface. Literally every car since about 2000, certainly in Europe, has had this fitted. And there are different protocols that are used through that interface in terms of the way that messages are sent. So the basic set of messages are things like the throttle position, engine speed, those types of things, which are primarily designed to give you information about how the engine is performing from the point of view of emissions, because that's one of the big things, obviously, the Europeans are concerned about is how much carbon dioxide, nitrous oxide, all those types of things are being emitted by the car. There are other protocols that run there as well, so different manufacturers use different protocols depending on what the systems are they use internally. One of the most common ones is this ISO 15765, the Controller Area Network, which you may have heard of, which is called the CAN bus. And that's the way that all the messages are sent between the different parts of the system so that you can identify that this is a switch that's just been pressed and this is the signal that's being sent, or you've turned the heating up and so the knob's been turned to a particular level, that kind of thing. So it's all about messages being passed back and forth on the bus. So that's the sort of basics of computers and cars. Let's talk a little bit about the Raspberry Pi. So who here has a Raspberry Pi? Ah, lots of people, good. Now, the Raspberry Pi is a very interesting thing because if you look at the history of it, it actually started, the project started originally way back in 2006. And it's very relevant because here in the UK, one of the big problems that we have is teaching children about computer science. So I have a 7-year-old son, he goes to school, and he does ICT, Information and Communications Technology, as part of his lessons. What he does in that is learn about really advanced concepts like word processors and spreadsheets and web pages. And if he's really lucky, as he gets older and he gets into secondary school, they will teach him how to program in HTML. Now, I'm not sure about you, but HTML to me is not a programming language. JavaScript maybe is a programming language, but HTML most definitely is not. So the problem is that children are not learning about real computer science until they get to university, and that's a big problem that universities are seeing. So a number of professionals, a number of academics, primarily at Cambridge University, got together and they said they wanted to create something that would enable children to learn about computing. And they based this really on a project that was done by the BBC many, many years ago. And this was called Micro Live. Who's old enough to remember Micro Live? Okay, a few people. Who's old enough to remember the BBC Micro? A few more people. Okay, good. So that was based around the BBC Micro. Lovely machine, had a 6502 processor, 8 bits, a whole 32 kilobytes of memory. That's not megabytes, that's kilobytes of memory. And it was great. You could program it, you could do all sorts of interesting things with it, you could play Galaxians and all sorts of great things like that. And that's really where the Raspberry Pi came about. Now, Raspberry Pi is actually now 2 years old, and they've literally shipped millions of these things now. In fact, lots of people here have them. There's lots and lots of them in circulation, and people are doing some very interesting things with them. From the point of view of the specification, it is a nice, cheap, but reasonably low-powered by today's standards piece of hardware. So what you get is a little board. So this is a Raspberry Pi, if you haven't seen one. It's a little board, and you've got an ARM processor. So it's a fairly old architecture. It's the ARM 11 version 6, runs at 700 megahertz. It's Broadcom, single on-chip package. And one of the nice things that they've done is allow people to overclock it up to 1 gigahertz without breaking the warranty. I know I run mine at about 900 megahertz, not had any problems with actually doing anything with that. The current model comes with 512 megabytes memory. Initially it was 256, now it's 512. And that seems to be plenty of memory to do most of the things that people are doing with these types of devices. From an input and output perspective, there's an HDMI connector, so you can connect to TV rather than using a separate monitor. You've got an audio out plug. You've got 2 USB ports. You've got Ethernet. And then you've got a row of pins which allow you to connect all sorts of sensors and motors and things like that using various standards like GPIO, SPI, I2C, and there's also a serial connector there for a UART. In terms of the storage, there's no hard disk drive. You plug in an SD card, and everything runs off the SD card. So when it comes to looking at using this for a car system, it actually makes a lot of sense because there's plenty of computing power there. 700 megahertz, 900 megahertz, and half a gigabyte of memory is plenty for the kind of things that I've been doing with my system. The other nice thing about it is it's very low power in terms of electrical power. So it requires less than 1 amp at 5 volts, which means you can plug it into the cigarette lighter in your car through obviously a 12 volt to 5 volt converter. Don't plug it into the 12 volt supply directly. Use a converter, and then it will run quite happily from the in-car power system. Like I say, the persistent storage is provided by the SD card. And again, that makes it nice for an in-car system because if you've got a hard disk drive in a car where there's lots of vibration, lots of movement, that can be a problem. SD card, much more resilient in terms of vibration and being knocked around. Also for things like hot places and that kind of thing. It's also one of the things that we are supporting directly in terms of embedded Java. So we've selected the Raspberry Pi as a platform where we're going to support embedded Java, Java SE, Java ME, and make it so that people can use this as a cheap platform to get started with learning about embedded Java. So that gives us all sorts of things. We've done work in terms of improving the performance around using the hardware floating point processor as part of the Raspberry Pi. We've done some work around JavaFX and making sure that the graphics engine takes advantage of the GPU in the Raspberry Pi, and that all seems to work very well. So if we look at a little bit about embedded Java and JavaFX, So why we would use these types of things to develop this kind of application. One of the nice things about Java is that historically it comes from the idea of embedded systems originally. There was this, way back in time, there was this thing called the Star 7, which was really like the kind of precursor to the iPad in some ways. So it was designed to run in a device which had very small amount of memory. You know, literally 8 megabytes of memory was going to be a lot in those days. And what Java has done over time is we've kind of added different versions to it. We've tried to target it at different types of environments. And so if you look at the diagram here, right at the very, very small end, there's this thing called Java Card. And if you've got like a mobile phone, then you're running Java Card, because all the GSM SIM cards have Java Card on them. That runs in literally a few kilobytes of memory. Then for bigger devices where you've got maybe a megabyte of memory, then you can use Java ME. Now, obviously, a lot of people think of Java ME as being mobile phones. And clearly, we've not been quite so successful in terms of getting Java into smartphones. So we've decided that we're not going to focus on mobile phones. We will focus on embedded devices, things like sensors, things like gateways. But they still count in terms of the architecture from the point of view of Java Mobile Edition. And so in terms of the size, in the region of 1 to 10 megabytes of available RAM would be the kind of device where you would target that sort of platform. And then if you've got more than that, then you can start using the full Java SE environment, the one that we're all familiar with, and you can use Java SE embedded. So that's being ported directly to an ARM processor, and that will work quite happily in that environment. In terms of Java ME embedded, the current release is 3.3, and what this provides us with is a small version of Java to run in resource-constrained environments. So you have this thing called the Connected Limited Device Configuration, which is a basic virtual machine, and then a set of class libraries that you need in order to run your basic application. On top of that, there's a set of different profiles that you can add, which add different sets of APIs to address certain needs for different types of applications. And one of the things that we've done fairly recently is to include the Device Access API or Device I/O API. What that does is gives you a standard set of libraries so that you can control things like GPIO pins, you can talk directly to an I2C bus, an SPI bus, you can communicate with a UART and do serial communication, all from a standard library. There are other profiles that you can add, but this kind of gives us a basic idea of what we could use in terms of an in-car system. The other alternative is to use Java SE8 embedded. And as I say, this is an early access. We'll be releasing Java SE8 as part of the Java 8 launch later this month. You can download this from our website at the moment. You can run it on the Raspberry Pi, there's no problem. As I said, it's tuned for the Raspberry Pi environment, so the hardware floating point, the different compiler options are being used and so on. Also includes JavaFX. So if you want to write graphical applications using the Raspberry Pi, then you can do that with Java SE embedded. It's got compact profiles, which are part of Java SE8 to reduce the size of the footprint. Same idea as in Java ME, but slightly different in terms of the way that we've structured it. And we've also added this to our standard build platforms. So now every time we do an update in terms of like the Intel architecture or the Mac or Windows or whatever, then you also get an update in terms of the Raspberry Pi. JavaFX. Who's heard of JavaFX? Okay, most people, a few people. Right, JavaFX is really a replacement for Swing. So it's a way of writing graphical applications which is a lot more flexible than Swing. So you can do much more interesting things in terms of using a scene graph. You can do all sorts of effects. You can apply translucency. You can move things around, do translations in a much simpler way than you can with Swing. And what we've done is to include that as part of Java SE embedded. And so I thought, well, that makes a lot of sense because what I need is some kind of graphical representation of what I'm going to do with my system. A couple of things that are not supported on the Raspberry Pi as opposed to the full system. So there's no video playback. Well, okay, I probably don't need that in terms of what I'm building here. There's no support for the web component, so you can't have a web page rendered directly as part of your application. Again, I don't think for what I'm doing that's too much of a problem. One of the things you do need to think about is that in some environments you're constrained in terms of resources, so thinking carefully about how you design your application, how many nodes you use in your scene graph. And if you start making very, very complicated scene graphs with thousands of nodes, then you're going to find performance is an issue. But if you keep it down to a small number of nodes, as we'll see, you can actually do some quite interesting things. So let's talk about then building a Java-powered Carputer. And what are the actual details of that? Well, the first thing I wanted to do was to think about what were the design objectives of this kind of system. And really what I wanted to do was to add to the kind of information that you get in your car already. So if you look at the dashboard, you can see how fast you're going. So you have a speedometer. You can see how fast the engine is going because you have a tachometer. You can see how hot the engine is. There's a temperature gauge. You can see how much petrol you've got. But that's about it, really. Some cars will give you, a few extra bits of information. But really what we're interested in is let's get some more interesting kind of information. So things like how much power is the engine generating? What's the torque that we're getting from the engine at a particular time? What's the load on the engine? And then tie that into some of the driver data. So throttle position, maybe get the steering angle because there are steering sensors that are connected to the ABS system and the ESP. Braking force, again, that's the kind of thing that you can get information from the system if you know how to do that. And also I thought, well, let's measure the G-forces on the car. So we would need an extra sensor for that, and we'll see how we do that. But we could combine that, add the G-forces, and see what's actually going on. And then the other thing I thought was, well, rather than just having the information played on the screen as we're driving around, we could also record the information and then play it back later so that I can analyze my driving style, very Formula One kind of thing. I can decide, okay, I need to improve my driving style, use less fuel, that kind of thing. Now, as I said, the OBD2 interface allows you to plug something in which will give you access to the information that's coming from the car. And so there is this thing called an ELM 327, a little box that you can buy from eBay. And there are two main versions of this. One is Wi-Fi, one is Bluetooth. So the idea is that you plug it in, and then in the case of the one I've been using, it creates like a little Wi-Fi, not hotspot, but it enables you to connect to a Wi-Fi IP address using peer-to-peer connection, and then you can read data from that. Bluetooth, similar idea, except using Bluetooth rather than Wi-Fi. Prices are a little bit different. So the Bluetooth one is actually really, really cheap. It's literally less than £10. The Wi-Fi one is a little bit more expensive. It's about, £20 for that one. Uses fixed IP address in terms of how you connect to it. So you use ad hoc networking. In terms of configuring the Raspberry Pi to communicate with that, you have to edit the Etc network interfaces file. And then you can just say, okay, this is the address I'm going to connect to, and you just do peer-to-peer networking. There's no router involved or anything like that. What you then do is you communicate with it as a sequence of bytes or a sequence of characters. And it uses, in terms of communicating directly with the device, AT-style commands. Who remembers AT-style commands? A few people. Modems. So back from the good old days, AT commands are basically just a way of telling the box what you actually want to do. So you say AT and then something after it. If you send it a command which is not AT something, then it assumes that this is some kind of OBD2 command. It assumes that it is maybe a CAN bus command and things like that. So there are all sorts of ways that you can actually communicate with the systems of the car using this. The next thing I thought was, okay, we need a screen. And I need a screen that I can actually put in the car. So I found on eBay, and I really do like eBay because there's all sorts of wonderful things you can buy on eBay. And so I found this screen which was available on eBay. It was actually marketed as a Raspberry Pi screen because it had an HDMI connector for it. But the nice thing was it was also a 2-DIN fitting. And what that means is that for the sort of older style in-car entertainment systems, the sort of narrow ones, that's a 1-DIN fitting. So this was equivalent of 2 of those. And most cars will actually have enough room for this in them. Ideal for the center console. Originally, I had planned to remove my satellite navigation system and put this in the center console. So I actually bought like a fitting kit for that. But in the end, I haven't quite got around to that because I do find that the satellite navigation system is quite useful. And this is a little bit limited in its functionality at the moment. Has HDMI input, as I said, so you can connect it directly to the Raspberry Pi. And it's also got a USB connector so that you can have touchscreen events. So you can touch the screen, get where the touch happened, and use that as part of the application. Now, this was one of the first things I had to deal with. It was a bit of a problem with the touchscreen because when I plugged it in, I found that the Linux distribution I was using from the Raspberry Pi Foundation recognized it. So that was good. It had a driver for it, and it recognized it as a eGalax Inc. device. What it then did was it created two devices in the /dev/input directory, event 0 and event 1. And when I tried it with the desktop environment, it all worked fine. So I could touch the screen, I could move the mouse around, and that worked quite happily. But when I tried it with JavaFX, it wouldn't actually see any events. So I couldn't use the touchscreen with JavaFX. And I went back and I talked to the engineers in Oracle who were working on this, and they said, oh, it seems to be the problem is that JavaFX uses event 0, and all the information that's coming from the touchscreen is going to event 1. So I was like, well, we can do you a special build where we switch from event 0 to event 1. But then I was thinking to myself, oh, maybe there's a way around this. So necessity is the mother of invention. And I thought, okay, well, rather than doing that, we'll just delete event 0 and then recreate event 0 as the same device as event 1. So major and minor device numbers, you use this command mucknod, create event 0 as a character device with major and minor device numbers as appropriate. And then I just wrote a little script that ran every time you booted the system that would delete event 0 and recreate it. And that solved the problem. So that was all good. Got around that issue. From the point of view of the architecture, this is what we've got. So we've got the Raspberry Pi in the middle. There's the touch screen, which is connected to the HDMI. It's also got the USB for the touch screen going into the USB connector. There's a Wi-Fi dongle to talk to the ELM 327 device on the service port. The 12-volt car power supply going through a converter to give me 5 volts into the Raspberry Pi. And then an accelerometer, which I connected through the I2C bus using the pins that we've got on the Raspberry Pi. Now, what this looks like in terms of the box that I've got here, if we look inside, this is basically the sort of design. So I had the screen, and then I found there was a couple of sort of screw thread holes that I could use to mount the Raspberry Pi on there with a bit of perspex. And you can see here that this is, in my belief, any good software project should involve woodwork. So I've used woodwork here to put some mounting brackets in there. And the other thing you can see here is that I had trouble sourcing a short HDMI cable. So I needed an HDMI cable that literally was going to be about 3 inches long. And the shortest one I could get was about 1 meter long. So it's kind of looped around a few times and then sort of tucked in around the board. I did actually find a shorter one eventually, but in the end I thought, well, I've already done this, so I'll just leave it as it is. Accelerometer. So I found there's a nice little board that you can get from a company called SparkFun, and it's reasonably sort of not too expensive. It's about £40, I think, or no, maybe a bit less than that actually, $40 I think it is. So this is really nice because it's got 9 degrees of freedom, or 9 degrees of measurement, where it'll give you an accelerometer in all 3 axes, it'll give you a gyroscope in all 3 axes, and it will give you a magnetometer to measure the bearing that you're getting in terms of your compass reading in all 3 directions. So you can actually move the device around any direction and still get all of the information about where it's actually moving to. It's also got some built-in processing power that will take all this information and give you some sort of processed version of the data, but I haven't really used that. So far what I've done is just use the accelerometer and the gyroscope to get information about the speed of acceleration and things like that. From a point of view of using I2C on the Raspberry Pi, you have to first edit the etc modules file to make sure that the I2C support is enabled. And then if you use this I2C detect -y1, that will give you the address on the I2C bus of a device that's connected. And that way you can then talk directly to it. In terms of the code, it's not too complicated. You just have to look at the manual and then figure out the various bits and bytes that you've got to send. So this is, if you remember basic programming, this is a bit like peek and poke. So you get the I2C bus, you say I want to talk to a particular address on that bus, and then you write some bytes to the bus and to different registers on that bus saying this is what I want to do, so I want to start sensing, and you can also set the configuration of things like the gyroscope and the accelerometer, because the accelerometer will measure, I think it's 2G, 4G, and 6G as a scale. I figured 6G was probably a little bit of overkill for my car, unless I was going to drive it like into a brick wall. So I went for 2G, which seemed to be a good choice. And then you basically just read data from that, and it gives you the information about what's happening in terms of acceleration. One of the other things you've got to remember is compensating for gravity when you're dealing with acceleration, because the Earth does indeed suck. And what that means is that when you measure acceleration, there will be a constant acceleration in the vertical because of gravity. So you just have to compensate for that. And so the idea was that obviously you just zero out the gravitational effect. And the simplest way of doing that was to actually mount the box in the car so it was completely vertical. That way I could just say, okay, the acceleration in one axis is going to be constant, and then I don't have to worry about what angle it is compared to gravity and so on. Certainly for the purposes of the demonstration, that I think is good enough. You do have to think that in a more complex system, you'd have to take into account the fact that the car rolls going around corners, it dips, and it will actually move as you accelerate and brake. If you really wanted to, you could use the gyroscope information and then use a thing called a Kalman filter to compensate for the fact that it is moving and is off the vertical. Calculating power and torque. If you've got acceleration and you've got data about your car and you can find out how fast the engine is going, then you can calculate what the torque and what the power is that's being generated at any given time. So torque in Newton meters is the mass of the car times the radius of the wheel times the acceleration in G. And if you want to convert that to good old imperial units of pound-feet of torque, then you've got a magic number that you just multiply Newton meters of torque by. And power in terms of BHP is just the torque in pound-feet times the engine RPM divided by another magic number. So the things I marked in red are obviously things that we can measure reasonably accurately, but not super accurately. So we're not going to get a perfect result in terms of the torque and the power from this system. Obviously, the mass of the car is going to change a little bit because I can find out how much what's called the curb weight is, but then I have to compensate for the fact that there's a certain amount of fuel in there, there's me, there's other bits and pieces like car seats and stuff like that that I need to figure out. So you've got a reasonable estimate of what the mass is. Wheel radius, yes, you can measure that, but the wheel is not going to be completely circular because the bottom of the wheel is a bit flat because of the tyre. And the acceleration, because we've got the problems of going around corners and things like that. So we'll have a reasonable estimate at what we're actually getting in terms of power and torque. From the point of view of the software, having looked at the hardware, what I wanted to do was obviously come up with a design that would give me a way of representing the information that I got from the car. So I thought, okay, well, let's have a screen-based design. So we'll move between different screens to display different sets of information. Start off with a splash screen. We'll have some basic data from the car, some advanced data. Then, because we've got the accelerometer, we can also have G-forces and measure that, see what's going on. And to give us an idea of how things are changing over time, we'll use a graph to represent a sequence of values and see how things have changed. Obviously, we want a simple user interface. If I just put up a set of numbers, it's going to be very difficult to read that whilst you're actually driving and stay safe. So you need some other way of representing the data. And also how you interact with it, you need to make sure it's simple because obviously if you've got a complicated user interface from how you actually talk to it, then you want to make sure that you're not doing anything where you're trying to do something as you're driving. So I started looking at what other people had done and get some ideas from that. So this is a Renault Megane Sport. This is the older one on the left, which gives you things like the boost pressure on the turbo, the throttle position, torque and power, also tells you what gear it's in. And then they've got a newer version which is more colourful and gives you some nice sort of graphs of like G-forces that are involved. If we move up the scale a bit, this is the Tesla. And I was lucky enough to actually go for a ride in a Tesla last year. And it's lovely because it's got like this 18-inch flat panel display in the middle, which gives you all this information about what's happening with the car and how it's being charged and things like that. So you can really sort of go to town in terms of the interface that you design. And then if you go to the real extreme, this is the display from the Lamborghini Revuton. And this is where you're into like, Battlestar Galactica, kind of like Starship Land. And I look at this and I go, I don't actually know what most of these things actually mean. So they've got a really kind of funky idea of how to do the tachometer. So, you've got two graphs on either side with the number of revolutions per minute. And then the middle changes to show you which gear you're in. There's some kind of circle here, which I don't quite know what it does. And then there's like a little sort of diagram at the top. Again, it's not quite clear what that does. So having looked at all these, this is what I came up with. A little bit simpler. But important to be simple. So I thought, okay, well, let's do sort of a simple bar chart where we can see a value and make it simple from the point of view of the UI design. This only needs 3 nodes by default. So you have one rectangle for the outer box, you've got one rectangle for the value, and then a red line which you can use to indicate what the maximum value is you've hit so far. And then if you want to, you can also add some numbers, which would clearly add some optional nodes as well. So this is easy to see because if you look at it quickly, you can see immediately, what percentage of the total value that represents. So there's no numbers that you have to look at constantly. It's quite a simple way of registering information. Then I looked at, okay, so in terms of the UI, keeping it simple again, sequence of screens, let's just go with the idea of one touch to change between screens. So there's no like trying to find a particular button on the screen or sliders or anything like that. It's just you touch the screen, it moves to the next screen. And we just loop through a sequence of screens to get the information. Don't want a menu. Again, it's too complicated, so we'll just go for a very simple kind of approach. And the one thing I found is obviously in terms of the way that we process that, we need to make sure that the mouse events get sent to the relevant part of the display so that it can detect when you want to change screen. The other thing I thought about using was the steering wheel buttons. So repurposing some of the existing buttons and saying, okay, when I press that button, then I'll change the value on the screen. Haven't quite got that far yet because, and we'll come back and talk about CAN bus a little bit later on. So this is the splash screen that I came up with. So I basically took a photograph of my satellite navigation system and then photoshopped it to add Duke and the Java logo to it so that it would have a nice looking splash screen. Then I created a basic data set of results. So this is showing the engine load, the intake temperature for air coming into the engine, the catalyst temperature for exhaust going out, current throttle position, and also the pressure of the fuel going into the engine. So this is the sort of basic data that you can get from the engine. Then turn that into some advanced data. So again, got throttle position as before, got the engine speed now, and also the calculated torque and power output from the values that we created, well, maths that we used earlier. Then I thought, okay, for G-force, let's use, it's a little bit difficult to see on this diagram, but the idea here is that you've got a series of circles which show you how you're accelerating in a particular direction. So the up and down is basically acceleration forward and backwards, so depending on whether you're accelerating or braking. The left and right is clearly whether you're accelerating going around a corner, so left and right. And then the bar on the right is the acceleration in the vertical, so you can see as you go over like a speed bump or something, you'll see the acceleration as you go up and down that way. And I don't think you can actually see it, but there are some green dots on here which represent the sort of the maximum that you've achieved in a particular direction. And hopefully we'll see that when we show the demo later on. And then, like I say, we can graph some results and show, okay, this is throttle position as I'm driving along, just some random data to see how I'm driving over time. I mentioned the idea about using the steering wheel buttons. One of the things you find is that you can monitor the CAN bus. So you can see all the messages that are coming on the CAN bus. So in theory, you can see all the messages that are coming from the buttons, from the satellite navigation system. You can talk to the center console and say, I want to display this piece of information. You can get the steering wheel position, all that kind of thing. Problem is that the car manufacturers are not keen on sharing this information. So you can't just go to the car manufacturer and say, give me all the details about the CAN bus that you use and get all the data for that. So you literally have to reverse engineer everything. And that means piling a load of data, looking through it and trying to figure out where you've pressed a button and what that actually results in terms of the message that's being sent on the CAN bus. I haven't quite got around to doing that in detail yet. That's the next part of the project, really. A few ideas I've got for the future, and also some conclusions and resources before I show you the demo. So one of the things I've thought about is integrating a heart rate monitor. I thought it'd be fun to actually monitor my heart rate as I'm driving around. So you can see, match your heart rate against G-force and, as you're accelerating and things like that. Also, I'm kind of intrigued by the idea of a heads-up display and using like a half-silvered mirror on the screen and using like a micro projector to project information onto the screen. CAN bus signals, like I say, it'd be really interesting to do more work around that and try and figure out things like the brake pressure, steering position, all those good things. And ultimately, so you can send commands as well as read them. That's a bit scary, though, because if you start saying, I want to brake right now, or I want to change the way something works, that could be potentially very dangerous. There's a lovely demonstration I saw of somebody who had it was like a Toyota Prius, and it was one of the ones that had the self-parking system built in. So there was a motor that would actually drive the steering wheel. And what they'd done is they had like a Nintendo Game Boy that was talking to one of these boxes connected to the system. And they could actually drive the car using the Game Boy. Security is something that is obviously not a major concern at the moment, because you can just plug this in and there's no issues around just being able to send messages, read messages, and that sort of thing. So it is something that I know car manufacturers are looking at in more detail for future systems, because the more these things get connected, the more you have the ability to talk remotely to these systems. We do have to figure out how to make them secure. One other thing that I've been working on recently is the idea of a GPS sensor, so you can also combine information about the position. So this is just a GPS sensor I got from Adafruit, and that connects very easily to the Raspberry Pi using the serial connection. And then I also got another little board which talks directly to the CAN bus. So rather than having to go through the service port, you can actually tie directly into the CAN bus on the car. So that means taking the satellite navigation system out and just splicing into some of the wiring on the car, which I haven't done yet because it's a lease car. So I don't know. They might frown upon that. Place to go for more information. Obviously, you're an Audi fan, then Audi.com. RaspberryPi.org has lots of information about the Raspberry Pi. Has lots of forums, and there's all sorts of discussions around lots of different things. JavaFX.oracle.com, and I've got a blog which I do need to try and update at some point, which I've started writing about what I've done with this project, so you can find more details there. Like I say, I do need to update that a bit. So let's just spend the last couple of minutes and just show you a couple of demos. So what I'm going to do is, let's switch to this. So the first thing I can show you is, no, not that. So this is a video that I took with the help of Steve, who I think is in the back. So the idea here was to actually video the system in action in a car. So if I just run this, and let's go to, no, that's not what I want to do. Okay. There we go. So this is basically, it's a little bit, the projector's not great, but so this is just driving around the car park in the Oracle office, and you can just about make out the bar charts moving there. I'm not going to show you too much of that because the brightness is not very good on the projector. But you can see this is basically the idea. So it's mounted on the screen, mounted on the dashboard, and then you just touch the screen, and it changes its view. So if I just come out of that, because that's you can't see that at all. So let's stop that. Okay, so what I will do is I'll show you on this system here. Hopefully you'll be able to see this. Is if I go here and run this. Right, so what I've done is I've set my laptop up so that it will actually work as the source of the data. And then on the display here, I go, yeah. So it'll take a couple of seconds to start up. Hopefully you'll be able to see this. Yeah, it does take a few seconds to start up. We'll go through a bunch of messages and things. And then eventually it will start up. One more message. There we go. Okay, so that's the splash screen. And then we should get, yeah. So now what you're seeing is playback of the data from my laptop of pretty much the same run that we were looking at. And then if I touch the screen, what that'll allow me to do is, hopefully, touch the screen. There we go, yeah. Change the display, so that's the advanced data. And we've got the G-force as that bounces around. Each of the circles represents half a G. So I managed to get, I think, just over half a G in some directions, but not much beyond that, which is not really surprising. And then, obviously, there's a graph. This is the throttle position, so you can see how much the throttle is being used. I found this quite interesting because you find that you actually use the throttle surprisingly little most of the time, and then suddenly you do accelerate quite hard, and then suddenly it goes up quite a lot. And then, just like the last bit, so that's just the power output. I think we've got the scale on this graph wrong, so it probably needed to be a different scale. But again, you kind of get the idea. And then I had to have a thing so you could actually get out of it. So there's a big exit button on one screen. But that basically shows you the idea of how it works. So let me just, actually, hang on. I'll just exit out of that. Right. Because the other thing I can do is, so I'll just run this on here, and then see whether that actually works. So that should then run the same thing, but on my laptop rather than, there you go. Oh, that's much better. You can actually see that now. So that's essentially the same thing that's running on the box. And then you can switch between screens and see the values. And that's the G-forces. And you can see that. And then the graph of the data. So were there questions? Because I've got about 2 minutes, I think. Okay.
So this is the same question.
Okay. You mentioned the problem with ICT teaching in the UK. Have you seen the new national curriculum? If so, what do you make of it? I must admit, I haven't had a great deal of look at that. I know they are working on changing the national curriculum, and hopefully the changes that they're making will make it easier with using things like the Raspberry Pi. Have you tried to read from the bus directly? Not yet, because that's the little card that I've got, the CAN bus card. So I will be trying to do that. Your splash screen references Audi MMI. Is that the same as the Audi? No. So the MMI is just the satellite navigation box on the car. The OBD2 port is the one that you actually plug in underneath the dashboard. So it is a different thing. And how much did the whole thing cost? It wasn't too expensive. Yeah, you can see I accelerated quite hard there. It wasn't too expensive. The Raspberry Pi, obviously standard Raspberry Pi price, few bits and pieces in terms of the box and the cabling and stuff. The screen was probably the most expensive. That was just over £100. You can get cheaper ones now. I've seen a lot that are coming out now which are cheaper. So if you want to get one, you don't have to get this particular one. You can find cheaper screens that are actually touch screens as well. Adafruit do quite a small one. So if you wanted to make a smaller one, which was literally only about $35, $40 now. So you could, in theory, build this for under £100 without too much problem. So with that, I think I've run out of time. So unless there's any other questions, people want to...
Yeah, I would have one really quick question. Why go through all this trouble and not use an Android phone that will give you a screen, accelerometer, and programming in Java, and a nice interface?
Okay, I'll explain that one. Let me just come back to my slides, and I'll point that one out to you. It'd be this bit here, Oracle. So yes, I mean, I could have gone down the Android route, but that doesn't quite fit with my business model. Because I'm Oracle, we do Java, and we don't do Android.
If you have to kind of change your system, not work with the car, but with another mechanical system which is moving up and down and rotating,
Yeah.
right? And that's small. Things like motion detectors.
Oh yeah, I mean, in that case, you could certainly use, I mean, the sensor that I've used is fairly broad in terms of its application, but you can get much more sensitive sensors for different applications. And because the Raspberry Pi and Java supports things like the I2C bus and SPI, these are very common ways of connecting to those types of sensors. So you just change the sensor that's involved. So there's all sorts of different approaches you can take. But yeah, you could tailor it to a different kind of environment very easily, yes. Okay, one more question. I'll make this the last one.
How difficult is it to reverse engineer what's... Do you just have to sit there with your foot on the throttle and go, I have to see the throttle? Or have you, I mean, is there any indication at all in the messages what they are?
Basically, all the CAN bus messages consist of like a device ID and then a sequence of bytes, which are the message that's being sent from that device ID. Or there's like a device ID from and a device ID to. So if you're sending a message from A to B, and then a data packet. So the actual format of the messages is easy to decode. What the tricky bit is, as you say, you get like a stream of these messages. And the way I've seen other people do it when I've looked on forums is that you basically record a bunch of data and you say, okay, I'm going to press this button 5 times in a row, or I'm going to press the accelerator and make it change a lot over this period of time. And then you've got to try and figure out from that which is the message which ties into that event. And then once you've got an idea, you go, okay, I only look for that particular message, and then you test your thing to see whether it actually works. So yeah, it's not simple. It'd be much easier if Audi would just give us all the details of the message.
No online where someone's already done this work.
No, and I tried a number of different avenues of research, and nothing came up from that. Okay, so thank you very much.